Welcome, I'm Rebecca Weaver. I'm going to be discussing first and second derivative tests and curve sketching today. For our curve sketching, we have a general approach. It's a four-step process. We're going to start with f of x, and we're going to compute both the first and the second derivative. Next, we'll locate all the relative maximum and minimum points and make a partial sketch. Then we're going to study the concavity of f of x and locate all the inflection points. Step 4, we'll consider other properties of the graph, such as intercepts, complete the sketch, maybe do a point or two, maybe a few points. We'll need to define critical values first. Given a function f of x, a number a in the domain such that either f prime of x equals 0 or f prime of x is undefined. So we'll need to find those values. For the function below, notice that the slope of the function is 0 at x equal negative 2, and the slope is undefined at x equal negative 0.4. Notice that the function has a relative minimum and a relative maximum at these points. The first derivative test for local extreme points says that if you have some first derivative, f prime of a equal to 0, if f prime changes from positive to negative at x equal a, then f has a local maximum at a. We can look at that figure and see that our function had a slope that was positive, then it was negative. So it went up, then it went down, therefore we have a local maximum. If f prime changes from negative to positive, meaning that we go down, then up at x equal a, then f has a local minimum at a. And that's what that picture represents. If f prime does not change sign at a, meaning that f prime is either positive on both sides of a or negative on both sides of a, then f has no local extrema at that point. So that just means our slope was positive, might have gone to 0, but then it was still positive again. So it was going up, it kind of petered out, and then it went up again or down and down again. And that's what those graphs show you. So let's do an example using the first derivative test. We need to find the local maximum and minimum points for this particular function. F of x equals 6x cubed plus 3 halves x squared minus 3x plus 3. First, we find the critical values and the critical points of f. So we have to take the derivative. So in taking that first derivative, we're going to have that f prime of x equals 18x squared plus 3x minus 3. We need to find where this first derivative either equals 0 or is undefined. So we'll factor it, and we'll see that it equals 0 when x is 1/3 and when x is negative 1/2. Therefore, those are our critical points. Substituting the critical values into the expression for f, we get what those points are. So we're going to have the point x equal 1/3, and plugging that into our original function f, we get 43 over 18, doing the same thing with negative 1/2. We get 33 over 8 after all of that computation. Therefore, the critical points are 1/3, 43 over 18, and negative 1/2, 33 over 8. To tell whether we have a relative maximum, minimum, or neither at the critical point, we're going to apply the first derivative test. Now, this requires careful study of the sign of f prime of x. That's the slope. So we need to know if the slope's going up or down. And that's going to tell if it's a maximum or minimum. Now, we can make a chart. It's going to be kind of wordy as to how we set up the chart. You might like it better once we actually do set up the chart and I talk about it. But here's how you set it up. You divide the real number line into intervals with the critical values as endpoints. Since the sign of f prime depends on the sign of its two factors, 9x minus 3 and 2x plus 1, determine the signs of the factors of f prime over each interval. Usually this is done by testing the sign of a factor at points selected from each interval, just random points in that interval. They'll all have the same sign. In each interval, use a plus sign if the factor is positive and a minus sign if the factor is negative. Then determine the sign of f prime over each interval by multiplying the signs. So since this was two factors, that we'll have two signs that are multiplied together. A plus sign of f prime corresponds to an increasing portion of the graph f, and a minus sign corresponds to a decreasing portion. Denote an increasing portion with an up arrow and a decreasing portion with a down arrow. The sequence of arrows is going to give you the general shape of the graph, and in particular tell you whether or not your critical points correspond to extreme values. And really, just look at the graph. And you have a graphing calculator too. So we have these critical points. I'm going to set up my table. You'll notice I have my two factors, 9x minus 3 and 2x plus 1. I'm going to plug some number in where x is less than negative 1/2. Any number that's to the left of negative 1/2, you could do negative 2, negative 3, negative 50, doesn't really matter, but when you plug those in, you will get a negative for each of those two factors. Multiplying those together, you will see that you have a positive slope, so that means it's increasing on this interval. Plugging in some number in between negative 1/2 and 1/3, my favorite number is 0. This factor here, 9x minus 3, is negative. The 2x plus 1 is positive. That would give me a negative slope, meaning that my function is decreasing on that interval. Carrying on further, x greater than 1/3, just pick any number, say 5. If you plug in 5, you'll get positive all the way across, and we see that it is increasing on that interval where x is greater than 1/3. You can see from the chart that the sign of f prime varies from positive to negative at x equal negative 1/2. Thus, according to the first derivative test, f has a local maximum at x equal negative 1/2. Also, the sign of f prime varies from negative to positive at 1/3. So f has a local minimum at x equal 1/3. In conclusion, f has a local maximum at negative 1/2, 33/8, and a local minimum at x equal 1/3, y equal 43/18. You can see from the, upon analyzing the various intervals, and had any two consecutive intervals not alternated between increasing and decreasing, there would not have been a relative maximum or minimum at the value for x separating those two intervals. Next, we have the second derivative test. The second derivative test for local extreme points. If f prime of a equals 0 and f double prime of a is less than 0, then f has a local maximum at a. If f prime of a equals 0 and f double prime of a is greater than 0, then f has a local minimum at a. So that means if our slope is 0, then if the second derivative tells you that it's negative, then you have a local maximum because it's concave down. And if our slope is 0 and our second derivative is positive, we have concave up, therefore you have a local minimum. So we need to locate all possible relative extreme points on the graph of the function f of x equals x cubed plus 6x squared plus 9x. Then we'll check the concavity at these points and use this information to sketch the graph of f of x. Now right now we've got our derivative. We have our first derivative and then we have our second derivative. We computed that. We need to find our critical values. We'll use the first derivative to find our critical values and factor. From this factorization, you can see we're going to get that x equals negative 3 and x equals negative 1 to be our critical values. So there, I have it there. In other words, the graph will have horizontal tangent lines when x is negative 3 and x is negative 1 and nowhere else. To plot the points on the graph where x is 3 and negative 1, we're going to substitute these values back into the original expression of f of x, and then we're just going to compute. So I need to compute the x and y values at those two points, and then I will get those 2 points once I crunch those numbers. When I plug in the negative 3 and the negative 1, I get the points negative 3, 0, and negative 1, 4. Those are possible maximums and minimums because maximums and minimums are critical point. Next, we check the sign of f double prime of x at x equals negative 3 and x equals negative 1 and apply the second derivative test. So when we plug those values into our second derivative, we find that at x equals negative 3, our second derivative is less than 0. Therefore, we have a local maximum. When we plug in x equals negative 1 to our second derivative, we find that it is greater than 0, meaning that we have a local minimum. We're going to sketch this, plugging in those points and sketching, and I see that I have a concave down and a concave up. In order to find inflection points, we just set the second derivative equal to 0 and solve for x. Kind of like critical points. Critical points are the first derivative, places where the first derivative is 0 or undefined, and for inflection points is where the second derivative is 0. So we're going to sketch the graph of f of x equals x cubed minus x plus 2. We need to find all of those different derivatives, the first and the second derivative, and we do that. Then we're going to find our critical points. In order to do that, we set the first derivative equal to 0, and we will find that our critical values are positive, negative square root of 3 over 3. We're going to need to substitute these values of x back into f of x, and we're going to find that after that computation, we get some sort of decimal number. We definitely aren't going to be plotting that, so we would probably want to change that to a decimal. Then we're going to compute those values of square root of 3 over 3 and the negative square root of 3 over 3 to see if we have local maximums or minimums. For the first one, we find that at the second derivative, the positive value, the square root of 3 over 3, we find that it's greater than 0, so we have a local minimum. If we plug in the negative square root of 3 over 3 into our second derivative, it will be negative, meaning that we have a local maximum. Since the concavity reverse is somewhere between the square root of 3 over 3 and the negative square root of 3 over 3, there must be at least one inflection point. So in order to find this, we're going to set the second derivative equal to 0, and then we find that that's going to happen at x equals 0. Pretty symmetric there. So the inflection point occurs there. In order to plot the inflection point, we just find that value, plug x equals 0 into our original function. We'll get that y is 2, plot that point. Here is our sketch of that graph. And I probably wouldn't have known where square root of 3 over 3 is and where this thing was. I would have had to have changed this to a decimal number. But anyway, that is what they are exactly. So, but I mean, if I was plotting them on a piece of paper. Anyway, if you have any questions, you be sure and let me know. Send me an email, rweaver10@alaska.edu. Thank you and have a wonderful day.